Okay. Well, so my name is Charles Mobley Thompson from Berkeley. Introducing myself, I guess. My talk is about gauge symmetry, dynamics, and anisotropic gravity. So the goal of this particular piece of work was to explain basically how to there we are, reproduce the low energy spectrum of general relativity in an anisotropic model of gravity. Okay, before I can do that, I have to answer the question, what is anisotropic gravity? So the original idea behind anisotropic theories of gravity, also called gravity at a Lifshitz point or Rorschach-Lifshitz gravity, is to combine gravity with the idea of anisotropic scaling. So in condensed matter systems, you frequently have many condensed matter systems that are characterized by scaling symmetries, but scaling symmetries which are anisotropic. So if you rescale space by some amount lambda, you don't rescale time by the same amount, but rather by lambda to some power z. And z is called the dynamical critical exponent. So theories of this type have a number of properties that differ from relativistic theories that physicists, high energy physicists, are more accustomed to. One of them is it improves the high energy behavior of the propagator. That basically means that theories become more renormalizable. Okay, why should this be interesting in the first place? Well, one reason it could be interesting is this property of improved ultraviolet properties. And that gives you the possibility of making theories, interactions, which aren't renormalizable in Lorentz invariant theories, renormalizable. And of course, the most sort of notorious theory that we would like to have an ultraviolet description of is quantum gravity. So there's the possibility, since these theories are at least power counting renormalizable. Of course, whether they're really renormalizable is a much more difficult question. But because they're power counting renormalizable, that raises the possibility that we can find an ultraviolet completion of some theory of gravity. So if this is true, then you could ask various questions. Could you apply it to phenomenology? Goes to physical setups. Try to do some kind of ultraviolet completion of the standard model. There are various issues with that, such as making the speed of light of all particles the same in the infrared, which I can mention a little bit more later. A second thing of interest is, so in string theory, people look at the Polyakov action, and which basically boils down to doing quantum gravity on the world sheet of the string. In M theory, people are interested potentially in membranes, and membranes have the problem that they do not behave well in the ultraviolet if you try to quantize them. And so if you can do gravity, an ultraviolet completion of gravity of some sort on a membrane would be a construction of some interest. You can also ask if a gravity model of this type, if you could run some of the same ideas from the ADS-CFT correspondence, and perhaps find a duality between these sorts of gravitational models and other theories, especially perhaps non-relativistic field theories, which have been of some interest recently. There are also connections between these theories and the theory of Ricci flow, as occurred in the proof of the Poincare conjecture. Oops. Okay, so let's start with a simple example. That is the Lifshitz scalar. So the Lifshitz scalar theory consists of just the basic theory consists of a time derivative squared, and rather than having a gradient of phi squared, instead you have the Laplacian of phi squared. So in this case, the dimension of the field phi is equal to d minus 2 over 2. And that means that the critical dimension in this theory, the dimension where you have an infinite number of marginal and relevant operators, is is two spatial dimensions. D here is a number of spatial dimensions. The total number of dimensions would be 2 plus 1. So if you're looking at marginal couplings, that's like doing nonlinear sigma models in 3 dimensions, 2 plus 1 dimensions. And the relevant couplings are like doing linear sigma models. Okay, so if we apply an idea like this to gravity, the starting point is to try to write down some kind of action that has a sensible idea of metric, but at the same time includes anisotropy between space and time. And the way we start is by writing down an action which is quadratic in time derivatives of the metric. Now, the reason it should be quadratic in time derivatives is that higher derivative theories also have higher derivative theories that are relativistic, that have local or global Lorentz invariants, are better behaved in renormalization theory. But they also have problems in quantum mechanics because the presence of higher time derivatives typically leads to problems with defining a positive definite norm on your Hilbert space, or a problem with unitarity. The two are basically interchangeable. So we want to restrict to the case where we have only 2 time derivatives, where we're much safer with the well-behavedness of quantum mechanics. And so we look at the most general contraction of, does this have a laser pointer or something? Is there any pointer available?
It should point.
It should point? Pointer.
We had a stick at some point.
Stick.
You know,
This projector really made me want a stick. Yeah. It's not absolutely necessary. But... Oh well, don't worry about it. I can just use my pointer finger. That's what it's there for. Okay, so we use the most general contraction of 2 time derivatives of the metric. And this uses, for those of you familiar with the ADM formulation of gravity, this is basically the DeWitt metric, except that it has an additional parameter lambda. And that's related to the fact that, well, in general relativity, the value lambda is fixed to be equal to 1 because you have arbitrary reparameterizations of your time coordinate.
Do I understand correctly that you consider only 3-dimensional metric, but not 1-dimensional?
So this case, so I mentioned the case of d equal to for the scalar field, but I mean this theory here is for d spatial dimensions in 1 time dimension.
Yeah, but the metric that you have in mind, is it spatial metric or?
Yeah, this here is the spatial metric. So I'll be talking about the pieces associated with the time component in a moment.
So the constraint, normally G00 is there for a Hamiltonian constraint. So
I'm going to get to
you
that.
will impose one.
Yes. Okay, but before we get there, the second piece of the action we have to write down is the potential term. And now that we're allowing larger numbers of spatial derivatives, we can include arbitrary powers and derivatives of the Riemann tensor.
Spatial Riemann tensor.
The spatial Riemann tensor, that's correct. Okay, so the thing I wrote down there, as you pointed out, this is purely the spatial metric. And so this currently is only invariant under spatial reparameterizations that do not depend on time. So it has no local symmetries. But we can introduce local symmetries by adding lapse and shift variables, which is basically adding G00 and G0I components to the metric, as in the ADM decomposition. And in order to respect as many symmetries as possible, you incorporate them by making the replacements here. So you basically replace the time derivative of G by the extrinsic curvature of spatial slices, and you replace the determinant of G by the determinant of G multiplied by the square of the lapse variable. And if you do this, then you end up with D local symmetries. And the D is the dimension of space, so we're in D plus 1 dimensions. And that means that we have local symmetries, but one fewer than in general relativity. So the geometry here is that of manifolds with foliations. So a manifold with foliation is defined in basically the same way as any other manifold, except that your charts are equipped with the preferred foliation by hypersurfaces, and your transition functions have to map slices to slices, or leaves of your foliation to other leaves. And so in gravity to Lifshitz point, we start with a spacetime manifold that has a preferred foliation by spatial slices. And our symmetry group can then be interpreted as the group of foliation-preserving diffeomorphisms that preserve that particular foliation by spatial slices. And so our symmetry...
What does all this mean for causality?
So as long as you have this foliated property, causality is perfectly fine. And basically, you have a preferred time coordinate, and things propagate.
Ordered, right?
Huh?
These leaves come with an ordering, say, which is next.
That's right. So of course you would have problems if you connected pieces back on themselves.
Local causality is fine.
But locally causality is fine. And so your symmetry transformations in a particular chart have this form. So if T labels your slices, and then the X label the directions along your leaves, then you can you have available in your symmetry group reparameterizations of spatial directions that depend both on space and on time, but reparameterizations of the time coordinate can depend only on time. That's the foliation that preserves the foliation. Now, n, the lapse variable, which is basically the square root of g upper 0, 0, can be a function of space and time. However, our symmetries only require it to be a function of time alone. So this gives us two possibilities we can look at. We can look at what's called a non-projectable model, where n depends on time and on space, or a case where n depends only on time. It's a projectable model. So this answers the thing that you were asking about before. In the non-projectable case, you do have a constraint coming from the G00 component. However, that constraint ends up being second class. I'll talk about that in a moment. And in the case where it's only a function of time, you have a constraint which is, you do have a first class constraint, but it's an integral constraint over all space. So it provides one constraint rather than a local collection of constraints.
Integrated Hamiltonian constraint, right?
Yes, it's exactly the integrated Hamiltonian constraint.
So the fact that second class, that's looking kind of bad at this point, matching to what we normally traditionally call gravitational degrees of freedom. Right?
Indeed. So if you relax this condition and you allow n to depend on space, then you have some additional things to deal with in terms of the second class constraint and closing the constraint algebra and so on. And it's a little bit hairy, and I'm not sure how well it's understood at this point. So at least as far as making sure that you have a constraint algebra that closes on a finite number of local propagating degrees of freedom, using the projectable case is a clear starting point to use.
What about just Newton's law, right? This is a 3 plus 1 theory, so now I could ask, this one 1 over r squared law for forces and so on. What do I have to do to get that?
I'm going basically to be talking about that in a moment too. That's sort of included in all this.
Power would turn up.
Oh yes,
because I was wanting to say
that would be helpful.
You can keep talking.
Okay, so all right. So let's look at a particular example. So at least up to total derivatives, the general potential we can write down, which has z equals to 2 scaling, is one which is quadratic which is a quadratic polynomial in the spatial Riemann tensor. And if z is equal to 2, then these coupling constants, alpha, beta, and gamma, and also the kappa squared out in front, the Newton constant, are dimensionless, which is basically the statement that the theory is power counting renormalizable. In general, if you have z, if you have scaling by z, then the dimension of kappa squared is z minus d, and so the critical dimension is d equal to z. You can also construct theories, for instance, a theory in 3 plus 1 dimensions, which is constructed from the Cotton tensor, which has a local anisotropic version of violent variance. Is another example. Okay, so now you have the question about what happens in the infrared. In other words, what happens on the scales on which we normally deal with gravity. And so to get a hint of what to do, we can go back to the scalar theory. And the scalar theory has relevant deformations given, for instance, by a term. We reintroduce the gradient square term, or we have a mass term. There will also be interactions. And in the presence of these relevant operators, at least if the mass is sufficiently small that you don't lose the field entirely, then this is the dominant piece in the infrared limit, and that means that so this theory, and this statement also includes the interactions which are marginal in the infrared limit, marginal or relevant in the infrared limit, is Lorentz invariant. So we have an accidental Lorentz invariance arising in the infrared. In the case of gravity, your relevant operators in the infrared, your two most relevant operators in the infrared are the Ricci scalar and a cosmological constant type term. And so that means that as long as we choose appropriate coordinates, this potential ends up taking a form which on integration by parts in the time-dependent piece, something that looks almost like the action of general relativity. Now remember that lambda constant I mentioned. That's one thing that prevents it from looking like general relativity. If lambda is not equal to 1, then it doesn't assemble into the four-dimensional Ricci scalar. But the contribution of this term to the dispersion relation is proportional to the momentum squared. So you end up with a dispersion relation which looks like a relativistic dispersion relation. And so we can ask the question, can we approach general relativity in the infrared? Or how closely can we approach general relativity in the infrared?
In regular general relativity, quantum is like one of those. You have anomalies in violent variance, or I guess the local Lorentz, and you can trade off, which you keep. Normally people keep local Lorentz and throw away the Weyl symmetry. Mm-hmm. I mean, could it be that what's happening here is you're really just keeping some sort of Weyl symmetry and throwing away local Lorentz?
No, I don't think that would match the stuff.
Not for any value of z, or.
I don't think so. I mean, maybe we can talk about it later. I can try to think about it a bit, but it doesn't. I don't think that would be consistent with the facts.
What happens with anomalies?
Huh?
What happens with anomalies in this picture?
Let's see. So generically, you're going to have, so typically speaking, you're going to have a different collection of anomalies which come from the ultraviolet behavior. So for instance, in the theory I mentioned before in 3 plus 1 dimensions, which is constructed from the Cotton tensor, in the spatial Cotton tensor, you would expect there to be anomalies in the anisotropic violent variance. Mm-hmm. But I haven't really thought about it.
Have people studied anomalies?
Not to the best of my knowledge, not in any appreciable detail. I mean, the thing is that in order to study anomalies, you usually, at least, if you're starting from a physics approach, you study anomalies by doing one-loop computations, and then seeing what happens. And the computations are sufficiently difficult in these theories that people that to the best of my knowledge, people haven't.
One loop should be.
One loop should be doable. I think that
And
people
yeah,
haven't actually. Well, okay. So there are some issues that need to be resolved first, and I'm also going to mention those in a moment. Let me continue, and then if you still want to discuss it after, that's fine. Okay. So this theory here, even in the infrared, it can't match general relativity exactly. One thing is that we would need lambda equal to 1. And the only way, since lambda will generically flow, the only way to get lambda equal to 1 would be to find some mechanism which requires lambda to flow to the value 1 in the infrared. And that does not seem very likely. The second issue is that, at least in the projectable case, n, the lapse function, is only a function of time and not a function of space. And of course, that is different from general relativity. In the case where n becomes a function of space and time, you have separate issues relating to the fact that the constraint that it generates is second class. And the third is simply that the gauge symmetries of the theory don't match. And in fact, because you have one less gauge symmetry in this theory than you do in general relativity, you're going to expect generically that you'll have one more propagating degree of freedom. And if you linearize the theory and you look at the spectrum, or if you do the Hamiltonian analysis, then you find that there is an extra degree of freedom, and that degree of freedom is a scalar degree of freedom. So you have a transverse traceless polarization of the graviton, and you also have a scalar polarization of the graviton. So this is problematic, and it would have to decouple from the theory in the infrared in order for the theory to actually reproduce general relativity. There's something that is perhaps even more peculiar, and that is that the dispersion relation, contribution of the Ricci scalar to the dispersion relation for the scalar mode, if your ultraviolet dispersion relation is healthy, it gives something that looks like minus k squared, and that means that signals an instability. So you have to, in order to try to match things in the infrared, you have to find some way of eliminating this instability. It's not an instability in the ultraviolet. It's the only problem in the infrared. So there are two ways we can try to deal with this. The first is just to ask the theory where it wants to go. So I'm going to go back again to the Lifshitz scalar theory. And in the Lifshitz scalar theory, if we add this marginal deformation, well, so the Lifshitz scalar field theory itself was developed to describe the tricritical point of water. And that's it's a point that separates three different phases: the ordered phase, the disordered phase, and the striped phase, or spatially modulated phase. And the striped phase arises when c squared is actually negative. And in that case, the phi equals 0 solution to the equations of motion is unstable. The time-independent solutions have to satisfy this equation, and the ground state actually becomes modulated in space. So you have spontaneous breaking of one of your translation symmetries. Incidentally, this is linear. If you want to actually stabilize a particular ground state, you just add interactions, and that will pick out a particular normalization of the modulated phase. In work that I'm preparing to publish with Peter Horjala, Patrick Zukowski, and Kevin Grosvenor, we can look at a theory of anisotropic gravity, and we can actually ask the question, what are its phases? So we try to ask the same questions that you ask about a condensed matter system of this sort. And when you do this, you actually find that the scale invariant, the anisotropically scale invariant theories, act as they're at the intersection between they're at the intersection of several different phase boundaries, and so, for instance, in one phase, if you look at FRW solutions that have positive spatial curvature, you have solutions that are similar to de Sitter, and those are your similar to these that are, you have solutions that oscillate in time. Those are sort of temporally modulated phases. Between those two phases, you end up with an Einstein static universe that's along a phase transition line, which satisfies the condition of detailed balance that I may mention more about in a while.
What does the word similar mean?
Similar.
To the setup.
Oh, it means that. Let's see. Need to remember the exact. I don't remember offhand if the form is, if it actually is literally a de Sitter space or if it.
You mean a 3 slice with some
It would be a particular slicing of de Sitter space. Yeah, it certainly has a similar behavior. I don't remember if the scale factor is actually identical or not, and that it probably depends on the parameters. Okay, so and we can also write down more involved constructions where we can explicitly find phases of gravity in which you have spatial modulation, time-independent solutions that are spatially modulated, and the ground state is not a homogeneous space. A second possibility is just to try to remove this scalar from the spectrum entirely. That would be the best option, because there are bounds on the number of graviton polarizations coming from pulsar from astronomical readings on pulsar stars in binary systems. How can we do that? Well, so as I said before, the presence of this extra scalar degree of freedom is related to the fact that we required n to be a function of time, or on the other hand, the second-class, first-class distinction, and the fact that we had fewer gauge symmetries. And so a natural way of trying to resolve the problem is to find another gauge symmetry to replace the gauge symmetry we lost, some sort of geometric or quasi-geometric symmetry that can perform the same task that the time reparameterizations performed in general relativity, as far as the spectrum is concerned. Okay, how can we hope to find such a symmetry? Well, there is an interesting observation that one can make. In the linearized limit of these anisotropic theories, there is an additional invariance under modifications of the lapse function by a total derivative of a function that depends on space but not on time. This is only a symmetry when lambda is at the value in general relativity. And therefore, if we require this to be a symmetry, it may be a way of forcing us to have lambda to make the kinetic term the same as the kinetic term in general relativity in the infrared. This is not a gauge symmetry in the sense we usually mean in physics. It's not a local symmetry because it doesn't depend on time. But it is a gauge symmetry. That's correct. That's correct. So this is a statement. This is a statement I make to physicists, because physicists usually have a habit of being sloppy about that kind of thing.
Well, that'll mean they'll struggle to remove the propagating mode, though, won't it?
Huh?
You'll struggle to remove a propagating mode this way.
That's the goal.
But won't you struggle because of this reason?
Yes.
Okay.
There is some struggle. Here the drama will unfold.
Oh, there's drama. Sorry.
Okay. This is reminiscent of the temporal gauge in electromagnetism. So if you choose A0 to vanish, then the Lagrangian of electromagnetism has this form here. So we gauge fix electromagnetism, and of course this theory here is not Lorentz invariant. But we obtain a theory that is Lorentz invariant by you have to impose the Gauss constraint, which
you
comes
have to carry the constraint along. That's right.
Exactly. So you have to impose the Gauss constraint in order to actually get the proper equations of electromagnetism. And this also has an invariance of this form. So you can modify the spatial components of the gauge field by a total derivative of a function that depends only on space and not on time. And this is a symmetry. This is a symmetry of this theory. So that suggests the possibility that that we could reinterpret our linearized anisotropic gravity model as a theory that started with a local gauge symmetry, but then we use that to eliminate one of the fields, and then end up with a constraint, and we've just forgotten to apply to carry the constraint along.
And then it better not be gravity.
Right. So there are plenty of questions you have to ask, but it's interesting to try to do it. So this suggests that we try to look for a gauge field that we can use to introduce a new symmetry in our theory. And we can start by looking at the non-relativistic contraction of the diffeomorphism algebra. So the diffeomorphism, if we do a 1 over C expansion, a certain 1 over C expansion, there are a number of different possible ones, but in a particular 1 over C expansion that is closest related to these anisotropic gravity models, we expand G00 as minus in terms of the lapse function, and then we would have subleading terms. But now we can include one subleading term, and we can ask what its behavior is under the symmetries of the problem. And what we find is that if we include the subleading corrections to the time reparameterization symmetry, so in the 1 over C expansion, the leading time reparameterization symmetry can only depend on time, not on space. That reproduces our situation. But the subleading term can depend on space and time, and it has the effect of generating these variations here. So your shift variable changes by a total spatial derivative, and this new A field here changes basically by a time derivative. So this looks very much like an abelian gauge symmetry. So what we try to do is we try to introduce a field which has transformation properties of this sort, and we see if we can generate, if we can manage to gauge the symmetry, the global symmetry that we have. Okay, and it turns out that if in the linearized theory, if we take the linearization of this term here, then the variation of the action under a symmetry that includes variation in time as well as space is cancelled by a term of this form. And so we can actually end up with a gauge symmetry. And then if you look at the spectrum of this theory, the extra gauge symmetry eliminates the extra propagating mode. It gives you a healthy spectrum, and the spectrum is the spectrum. The low energy spectrum is a spectrum of a graviton in 3+1 dimensions, a graviton which has 2 transverse traceless polarizations. Okay, we need to extend it to the nonlinear theory. But if we try to apply this to nonlinear theory, then we end up with extra terms, which are more complicated. So we end up with this thing here. And if we want this symmetry to be extended to a symmetry in the nonlinear theory, then we have to find a way to cancel this term here.
What was K?
K is the extrinsic curvature. Okay. Now, one thing you can notice is that this obstruction does vanish in several cases. So in 2+1 dimensions, well, in 2 spatial dimensions, the Einstein tensor, this thing here, vanishes identically. And so there's no obstruction. So if we're in 2+1 dimensions, we're already fine. It's a symmetry. A second possibility is a second possibility for trying to find an interacting theory is to forget the nonlinear theory and just try to generate an interacting theory of basically abelianized gravitons. Normally, you can't do that in the relativistic case because you can't generate. What was the issue? I think there's a problem with actually generating interesting interactions, basically. There are no I guess there are no marginal or relevant interactions.
You can still have a tree exchange, right?
I don't.
You should
I don't remember that. There's some reason that people just have completely ignored it. I don't remember
You
what
can
it
probably
is.
get the Newton law.
Yeah. Yeah. Well, the Newton law is very trivial when you don't have any matter.
You should
Right.
still be able to couple to matter at
You should still be able to
the
couple it.
three-point function.
Yes, you can couple it to matter just fine.
One particle.
Okay, so we can add a second possibility is that, okay, we added subleading terms in the expansion of G00. We can also try to add subleading terms in the expansion of Gij. And you can use this to close the, you can use this to eliminate the problem scalar, but you also remove everything else as well, and the theory basically becomes a topological theory. It has no local propagating degrees of freedom. So that's not helpful. So if we want a theory that has actual propagating gravitons in 3 + 1 dimensions, or some other number greater than 2, then we need to find a different solution to this issue. Okay. So we start by looking at going back to the nonlinear theory, and we ask, is the time-independent variation actually a symmetry of the nonlinear theory? And the answer is no. The obstruction is still present even in the case where you don't introduce time dependence. And in order to solve this, it seems we need to introduce yet another field, which Petter likes to call the Newton prepotential, and it transforms affinely under the gauge symmetry. Under the global gauge symmetry. When we include this term, we can now cancel the obstruction by adding a term of this form. Omega is a free parameter. I guess we usually write this with a 1/2, so this might not quite agree with the later slide. The variation of this term under this variation of nu cancels the obstruction, and we end up with the global symmetry. Okay, so now we have a theory that's invariant under this U1 sigma, the time-independent symmetry.
Over the new field.
With the new field.
Dynamical?
No.
Non-dynamical?
It's not dynamical. There's no way that you can make it dynamical in any interesting way that's consistent with the symmetry. Okay, and now we can gauge the symmetry by introducing our term from before, but now this omega has to match the omega that I had on the other slide. So it's just a relevant deformation. And okay, so this promotes the abelian symmetry to local symmetry. So we have another gauge symmetry, and now we ask, does this help us at all with our original problem? So let's look at the spectrum and see if it eliminates the mode. So you can do an analysis in the Hamiltonian formalism, and basically how it goes is just that you can show that A generates that varying A gives you a first-class constraint. Varying mu gives you a second-class constraint. And the gauge fixing along with the first-class constraint, once you work everything out, reduce the dimension of the physical phase space by 2 from what we had before we added any of the new fields.
And this is in 3, this is special 3 + 1?
This is D + 1. This works in D + 1 dimensions. It's just fine in D + 1 dimensions. Oops. And the net result is that it eliminates the scalar degree of freedom. And so what we're left with is precisely a transverse traceless graviton. And in the infrared, it has a healthy quadratic dispersion relation. It has a relativistic dispersion relation. And so then the spectrum of the theory matches the spectrum of GR in the infrared. So if you're in the infrared and you're at weak coupling, then the theories then the theories end up looking the same, at least in the pure gravity case.
This is still the linear theory, right?
No, I was talking about the nonlinear.
Just now-
Oh well, so I mean, when you go to the infrared in general relativity, then because R is because the interactions are all irrelevant, at least if you're above d equals 2. If the interactions are all irrelevant, then what you end up with, if you want anything at all, is just the linearized theory. So it is basically the linearized theory, and that would reproduce a Newton-like potential. Okay. So in addition to simply matching the spectrum, there's actually a certain amount of similarity between this and GR and the static solution. So a static solution requires that the covariantized time derivative, the extrinsic curvature of spatial slices, of the spatial metric vanish. And then the remaining equations of motion basically descend from a term of this form. And so if we just think of this term as being matched with the Laplace function from general relativity, then we end up with the same equations. And so the static vacuum solutions match those in general relativity. So what have we found overall? We've seen that anisotropic gravity with non-relativistic general covariance. So we've introduced a new sort of quasi-geometric symmetry that takes over for the missing gauge symmetry. It has some good features. So these gravitational theories, they have improved behavior in the ultraviolet, which renders them power countingly normalizable and possibly well-defined in the ultraviolet as quantum field theories. The spectrum and the static solutions also match those of general relativity in the presence of the new gauge symmetry. But there are a number of important questions that you have to ask about these theories. So first of all, the Newton prepotential, that function nu, is kind of peculiar. It's kind of strange the way it couples to the theory. What does it mean? Does it have some interesting geometric interpretation? How do you couple this to matter? One problem with this setup is that the presence of the gauge field A and the function nu make the way you couple to matter considerably more arbitrary. You have many more free parameters, and so it's not clear. It's not clear if there's a way of reducing the number of free parameters in how they couple to matter. Huh?
What about the equivalence principle?
Right. the equivalence principle is gone. Yeah. I mean, you sort of have you have an approximation to it in the infrared, but you know it sort of arises as a low order accidental symmetry.
Couldn't you impose it?
You should sell your theory as explanation of this neutrino space.
Yes.
Well, yeah. So actually, well, yeah. So here, there's a speed of light problem. So I mentioned before about the speed of light issue. So the dispersion relation is generally going to go something like omega squared equals k squared plus some parameter squared times k to the fourth plus and so on, which means that as things get faster and faster, the limiting velocity, the apparent limiting velocity in the ultraviolet becomes larger than the low energy limiting velocity. There is no limiting velocity, and so things can go faster than the speed of light, and that's kind of interesting in light of recent suggestions from the LHC. Although we'll see what happens with those. You can ask about cosmology and dark matter. People have written some gigantic number of papers trying to figure out what these types of theories say about cosmology and dark matter and dark energy and stuff like that. And apparently you can have some luck, but I don't really know any of the details. There you have it.
Thank you. So,
Questions? Yes.
Is there any sense in which the parameter z is observable?
Sure.
Theory described was actually the description of our world. Is there some measurement you can make that would tell you what z is?
In principle, certainly. I mean, you could tell just by basically by looking at you look at high energy. If you go up to high enough energies, then the contributions from the higher spatial derivative terms are going to become more important, and it will have a very definite physical signature.
Wouldn't other theories like string theory predict kind of higher order corrections anyhow?
Well, yeah, but they would look very different. You would definitely be able to pick them out in experiment if you could go high enough that they became important. So there's a question about what are the scales involved, and presumably if you're looking at a phenomenological scenario, then the scale at which these higher order terms would kick in would be something very large. I mean, you normally think Planck scale or something related to the Planck scale, and in that case, it would be very difficult to observe those higher order corrections.
The most interesting remark is that Lorentz symmetry can be accidental.
Yes. Lorentz symmetry. So I mean, this is pretty much generic in field theories, coming from the fact that Lorentz symmetry is the symmetry that comes from the simplest stable quadratic action that you can write down, and so then of course you wouldn't generically have low energy Lorentz symmetry, because although each individual particle would have a given speed of light, the speed of lights of different particles don't have to agree. So, for instance, that's basically what's behind Cherenkov radiation. If you have a charged particle that's going through a substance faster than the speed of light in the substance, then it radiates, and in that case, you sort of have a limiting speed of light, which is slower than the limiting speed of the particle of flavor that's passing through the material. So it is generic as long as you have a sufficiently high degree of symmetry. And so you can ask the question, is there some sort of symmetry principle you can introduce which would lock the speeds of light in the infrared? And it looks like you can actually, so supersymmetry is normally considered as a symmetry that's an extension of Poincare invariance. But it isn't really. Supersymmetry doesn't actually require the theory. A theory that's invariant under the standard supersymmetries doesn't necessarily have to be invariant under Poincare transformations, as long as you include higher order derivative terms. But the quadratic derivative terms are fixed, and that means that the relative normalization, i.e., the speed of light, is fixed by the supersymmetry. So that's one possible way you can try to lock the speeds of light in the infrared. And actually, if you introduce supersymmetry, you can suppress the Lorentz violations to a very large degree by having a scale of supersymmetry breaking that's not nearly as high as the Planck scale. And so that's a definite possibility for such a mechanism.
Isn't one just Lorentz that you're throwing away? It's really spatial. The full diffeomorphism group.
You're throwing away part of the diffeomorphism group.
You're throwing away space-time.
But what I'm talking about is trying to match. Is if you're asking about the real world and you're trying to match the observations you make, then the speeds of light of different particles are very similar to each other.
Space-time being a manifold is just a nice mathematical desire. So.
Yeah.
Are there any other questions?
Any other questions?
No? Speaker again.
That theories become more renormalizable. Okay, why should this be interesting in the first place? Well, one reason it could be interesting is this property of improved ultraviolet properties, and that gives you the possibility of making interactions which aren't renormalizable in Lorentz invariant theories renormalizable. And of course, the most sort of notorious theory that we would like to have an ultraviolet description of is quantum gravity. So there's the possibility since these theories are at least power counting renormalizable, of course, whether they're really renormalizable is a much more difficult question. But because they're power counting renormalizable, that raises the possibility that we can find an ultraviolet completion of some theory of gravity. So if this is true, then you could ask various questions. Could you apply it to phenomenology, to physical setups, try to do some kind of ultraviolet completion of the standard model? There are various issues with that, such as making the speed of light of all particles the same in the infrared, which I can mention a little bit more later. A second thing of interest is, so in string theory, people look at the Polyakov action, and which basically boils down to doing quantum gravity on the world sheet of the string. In M theory, people are interested potentially in membranes, and membranes have the problem that they do not behave well in the ultraviolet if you try to quantize them. And so if you can do gravity, an ultraviolet completion of gravity of some sort on a membrane would be a construction of some interest. You can also ask if a gravity model of this type, if you could run some of the same ideas from the ADS-CFT correspondence, and perhaps find a duality between these sorts of gravitational models and other theories, especially perhaps non-relativistic field theories, which have been of some interest recently. There are also connections between these theories and the theory of Ricci flow, as occurred in the proof of the Poincare conjecture. Oops. Okay, so let's start with a simple example. That is the Lifshitz scalar. So the Lifshitz scalar theory consists of just the basic theory consists of a time derivative squared, and rather than having a gradient of phi squared, instead you have the Laplacian of phi squared. Okay, well, so my name is Charles Mobley Thompson from Berkeley, introducing myself, I guess. My talk is about gauge symmetry, dynamics, and anisotropic gravity. So the goal of this particular piece of work was to explain basically how to reproduce the low energy spectrum of general relativity in an anisotropic model of gravity. Okay, before I can do that, I have to answer the question, what is anisotropic gravity? So the original idea behind anisotropic theories of gravity, also called gravity at a Lifshitz point or Rorschach-Lifshitz gravity, is to combine gravity with the idea of anisotropic scaling. So in condensed matter systems, you frequently have many condensed matter systems that are characterized by scaling symmetries, but scaling symmetries which are anisotropic. So if you rescale space by some amount lambda, you don't rescale time by the same amount, but rather by lambda to some power z. And z is called the dynamical critical exponent. So theories of this type have a number of properties that differ from relativistic theories that physicists, high energy physicists, are more accustomed to. One of them is it improves the high energy behavior of the propagator. That basically means so we want to restrict to the case where we have only two time derivatives, where we're much safer with the well-behavedness of quantum mechanics. And so we look at the most general contraction of. Does this have a laser pointer or something? Is there any pointer available?
It should point.
It should point? Pointer.
We had a stick at some point.
Stick.
You know,
This projector really made me want a stick. Yeah. It's not absolutely necessary. But... Oh well, don't worry about it. I can just use my pointer finger. That's what it's there for. Okay, so we use the most general contraction of two time derivatives of the metric. And this uses, for those of you familiar with the ADM formulation of gravity, this is basically the DeWitt metric, except that it has an additional parameter lambda. And that's related to the fact that, well, in general relativity, the value lambda is fixed to be equal to 1 because you have arbitrary reparameterization of your time coordinate.
I understand correctly that you consider only three-dimensional metric, but not one-dimensional.
So in this case, the dimension of the field phi is equal to d minus 2 over 2. And that means that the critical dimension in this theory, the dimension where you have an infinite number of marginal and relevant operators, is two spatial dimensions. D here is a number of spatial dimensions. The total number of dimensions would be 2 plus 1. So if you're looking at marginal couplings, that's like doing nonlinear sigma models in 3 dimensions, 2 plus 1 dimensions. The relevant couplings are like doing linear sigma models. Okay, so if we apply an idea like this to gravity, the starting point is to try to write down some kind of action that has a sensible idea of metric, but at the same time includes anisotropy between space and time. And the way we start is by writing down an action which is quadratic in time derivatives of the metric. Now, the reason it should be quadratic in time derivatives is that higher derivative theories also have higher derivative theories that are relativistic, that have local or global Lorentz invariants, are better behaved in renormalization theory. But they also have problems in quantum mechanics because the presence of higher time derivatives typically leads to problems with defining a positive definite norm on your Hilbert space, or a problem with unitarity. The two are basically interchangeable.